Next parameter, beam area. Beam area in polar two-dimensional coordinates, an incremental area dA on the surface of the sphere is the product of r d theta and r sin theta d phi, which is nothing but r square uh, sin theta d theta d phi. Here r square sin theta d theta d phi is nothing but d omega, which is a solid angle. D omega is nothing but d omega is a solid angle, which is expressed in steradians or a square degrees or a square degrees represented like this. So what is a steradian and what is a radian? We will look at into this very few minutes. So actually, the area of the sphere is area of the sphere is area of sphere is 4 pi r square. All this formula. Area of the sphere is 4 pi r square. I will show some formulas and standard notations. First of all, you please once look it into the picture. Antenna parameters. So beam area. So already just discussed it. So this is a three-dimensional spherical coordinate system. From this one, we want to calculate one parameter, that is a beam area. So this is the center of the point, which is a projection of. We want to calculate this particular area, which is in the form of a square shape. So incremental area dA is the product of the two components, that is r sin theta and r uh, r d theta and r sin theta d phi. These are the two components. So this is the product of these two things, that is a beam area. So we know what is this one. The area of the sphere is which is a standard formula 4 pi r square. So one steradian equal to, this is the standard one steradian equal to one solid, which is represented 1 SR, solid angle of sphere by 4 pi. So which is nothing but 3282.8064 square degrees. Now we will just see what is a radian and what is a steradian once. I will explain what is a radian and what is a steradian. Just a wait. The basic difference between a radian and steradian. Okay. Radian and steradian. Radian is a measure of a plane angle. Radian is about a plane angle, and while the steradian is steradian is about a solid angle. One radian is defined as the plane angle with its vertex at center of the circle with radius r that is subtended by arc. Again, one radian is defined as the plane angle this is the circle. So this is the center of the circle. One plane angle is defined as, one radian is defined as at the plane angle with its vertex at the center. Suppose this is the radius r, and okay, this theta is nothing but a radian. Arc theta of the circle. This is nothing but arc theta of circle. So here the total circumference of the circle is c equal to total circumference c equal to 2 pi r. So and what about a steradian? How can I represent a steradian? Means if you want to explain about steradian, it is a plane angle subtended by some arc. Suppose this is the center of the circle. So in similar way, the measure of solid angle is defined as steradian. One steradian is defined as a solid angle with its vertex at the center of the sphere with radius r that is subtended by a spherical surface area that is equal to square. That is, suppose at one point, sorry, if you want to calculate, if you want to measure only this area that is subtended by this arc, which is a spherical in shape, which is equivalent to the square with each side is equal to the square with radius r, then this angle, which is known as steradian. So here area equal to r square. This this complete as a three-dimensional picture. This pictorial comes into a square a little bit. Suppose a radius r. So the area of this one is r square. So this is the difference between a radian and a steradian. Radian and steradian. So now coming back to the picture where we are, and that is a complete scenario. So one steradian equal to, that is one SR equal to one steradian equal to 3282.8064 square degrees. We can represent like this. This is the standard one. So one what is this one? One radian, one steradian equal to this much of degrees. So now the calculation of the beam area. I will write some equations right now. All of you, please. The beam area or a beam angle, which is a solid angle of an antenna, is given by the integral of normalized power pattern over a sphere. Right? If you want to calculate the area, we need to integrate that system. Here the system is a sphere. The sphere area is 4 pi r. So that beam area of an antenna integral of, it is a we want to calculate for the three-dimensional system, that is there is a two notations, phi equal to 0 to 2 pi, and theta equal to 0 to uh, pi, and there is a power is represented by p suffix n, which is a function of theta comma phi d theta d phi. So we last time we have seen spherical coordinate system. Suppose this is a three-dimensional spherical coordinate system. So from this is a three-dimensional spherical coordinate system, we want to calculate the beam area. So it is a combination of it is a mixing of theta and phi. So in three-dimensional structure, one is a represented 0 phi 0 to 2 pi, and this one 0 phi equal to 0 to here. Suppose it is an x-axis and some it is a y-axis 0 to 2 pi, and if theta 0 to pi, so it is a 9. In this way, when we are going to write the formula, so spherical in beam area omega suffix a of an antenna phi equal to 0 to 2 pi and theta equal to 0 to pi, where the power is represented by Pn of theta comma phi sin theta d theta and d phi. And finally we write the equation, not finally, so many omega equal to double integral of, just you put here 4 pi Pn of d theta d phi. You know what is a d theta? Uh, mm, Sorry, I forgot here writing d theta d phi sin theta. So you know sin theta d theta d phi is nothing but a d omega, right? Just we spoke few minutes ago, where d omega equal to sin theta d theta d phi. So the beam area omega A is the solid angle through which all of the power radiated by the antenna would stream if the power maintained its maximum value over a beam area. Thus the power radiated is which is represented as the watts. Power represented as watts. Another formula for beam area is for mathematical calculations. You know, off power beamwidth is represented by theta off power. Off power beamwidth is represented by HP off power with respect to theta and off power with respect to phi. So the multiplication of these two will also get a beam area. This is a, what is this one? This is with reference to radians, degrees. This is with reference to steradians. This is about beam area and this is about beam area. Both are beam areas, radians and steradians. All right. So we will look into the one problem right now. We will solve one problem, right? Based on these formulas, we can do one problem, right? Find, what is the problem is, find the number of square degrees in a solid angle, in a solid angle of a spherical surface that is between theta equal to 20 degrees and theta equal to 40 degrees, and between 5 equal to 30 degrees and 5 equal to 70 degrees. So from as per the last equation, from the equations, beam area omega equal to integral 5. What is the range of 5 here? Integral 30 to 70. That is, it is, which is a 5, and integral theta 20 to 40. You know what is that one? Sin theta d theta and d phi. So sin theta d, this is about theta, so I put d theta here, just changing this one, sorry, d phi. So this is about a phi component and this is about a theta component. So from the mathematical calculations, we get 0.121 steradians if you do the mathematical calculations. Otherwise, by integrating and doing some mathematical calculations, we get 0.121 steradians. So 0.121 steradians. 1 steradian equal to, I have given some value in the last session. So 0.121 into 3283 approximately. So totally 397 square degrees. So this is one of the problem by calculating beam area. So beam area. Next one, next parameter. What is the next parameter? The next parameter is radiation intensity. Radiation intensity. The power radiated from an antenna per unit solid angle is called radiation intensity, that is represented by U. Again, the power radiated from an antenna per unit solid angle is called radiation intensity. Already last class, just now we have discussed about what is a plane angle and what is a steradian, what is a radian. So here radiation intensity is nothing but per unit solid angle, per unit solid angle. The antenna is radiating something. How much radiation, how much amount of radiation it is radiating is nothing but radiation intensity U. That is watts per steradian or watts per square degrees. So the normalized power pattern of previous section can also expressed in terms of this parameter. So we know radiation intensity is Pn of theta comma phi is nothing but radiation intensity. So Pn means power, normalized power. So from this one, normalized power can be expressed in terms of radiation intensity, so that U of theta comma phi by U of theta comma phi max. In last class, we write a term S, that is a Poynting vector, that is also correct. So S of theta comma phi by S of theta comma phi max, both are exactly right. So whereas Poynting vector S depends on the distance from the antenna. So here radiation intensity is watts per steradians. So one is about what we call steradian and one is about is called a radian. Okay. So the radiation intensity U is independent of the distance. Radiation U is independent of distance, right? So the power, normalized power can be expressed in terms of radiation intensity. What is the radiation intensity per unit per steradian? The antenna radiation is nothing but radiation intensity. Normally there is a one definition for density per unit area. Likewise, we are calculated. So then here intensity, radiation intensity per steradian, one antenna is how much radiation. So antenna radiation by steradian is nothing but radiation intensity. This is the thing. Okay, this is about radiation uh, intensity. Next one is a beam efficiency. Next one, beam efficiency. Beam efficiency. So beam efficiency, which is represented by this one. This is a simple formula. The total beam area is nothing but the total beam area equal to the main lobe area plus minor lobe area. This is a capital M and this one is a small m. And where about omega is nothing but beam area. So efficiency of an antenna is nothing but the main lobe area by total beam area is nothing but efficiency, beam efficiency. Again, omega suffix capital M. When a minor lobe area is neglected, this is the formula. Otherwise, total beam area, major lobe and minor lobe area by total beam area is nothing but a beam efficiency. So, so this is also a dimensionless. This is a dimensionless factor, dimensionless parameter. So this is this one. There is another formula, stray factor. What is a stray factor means? This is one formula which is represented by small m, epsilon small m. So minor lobe area by total area is nothing but a stray factor. So this is about some of the parameters which is all of you please study what is the radiation patterns, field strength pattern, power strength pattern, and illustrated problems, some illustrated problems, and uh, three-dimensional spherical coordinate system, off power beam width, first null beam width. Okay, and here today's class, beam area, radiation intensity, and beam efficiency. These are all some of the parameters. Next class we will look at into the some more parameters. Thank you.